Hello, my wonderful students and chemistry lovers. Today I'm going to talk to you about ion-ion interactions, and we're going to describe that using what we call the Coulombs law. My name is Dr. Lutano Wesley, and I'm going to serve as your guide today in this interesting lecture and conversation. Okay, when we talk about ionic compounds, it is important you know that sometimes we can also refer to them as salt compounds. Okay, and one incredible thing that we understood from our previous lectures is that ionic compounds are made when positively charged metallic ion, cation, is bonded to a negatively charged non-metallic ion by a strong electrostatic attractive forces known as ionic bond. And as a matter of fact, it is important to say that most ionic or salt compounds exist as solids at room temperature. And this cannot be alienated from the basic principle that we went through when we revisited the concept of kinetic theory of matter. Recall when we talked about kinetic theory of matter, we understood that particles of solid are more tightly packed together and more held together by strong forces of attraction, more than what we have in particles of liquid. More particles of liquid are more far apart than particles of solid, and in turn the particles of gases are most spread apart because they have the highest entropy. All right, so when you have particles that are held together tightly packed in place, most likely we're going to look at the phase of such matter to be somewhere in the neighborhood of a solid. Okay, so particles tightly held together in place by strong forces are most likely going to be solids. And this is the same principle that underscores the statement I made that most salt compounds or ionic compounds are solid at room temperature. It is important for me again to mention here that the atomic or molecular scale or level of things, okay, the attraction between opposite charges, okay, like we have when cations are bonded to anions to make an ionic compound, is the strong kind of interactive force that there is. I want to say it again. At the atomic level and the molecular level, okay, the attraction between oppositely charged ions are the strongest kind of interactive forces. And this is the basis upon which we stand and say that most ionic or salt compounds are solids at room temperature, since there is the strongest kind of attractive forces holding those particles in place. So at room temperature, those particles are very tightly held in place by the strongest kind of attractive forces known as electrostatic forces. So invariably, we want to describe the phase of most of this matter to be in solid phase at room temperature. I believe it's clear. Again, the strength of ion and ion-to-ion interactions is actually described using what we call the Coulombs law. And as a matter of fact, according to Coulombs law, okay, we know that the strength of the interaction between two ions is directly proportional to the product of their charges, which we denote as Q1 and Q2, and inversely proportional to the distance between their nuclei. Okay, that internuclear distance between ions is what we know as bond length. And as a matter of fact, the expression that helps us to describe the Coulombs law is E directly proportional to Q1, Q2 divided by D. Of course, we're here, we are talking about force of attraction or energy of attraction between ions. The energy of attraction or force of attraction or the attractive force between ions, denoted as E, is directly proportional to the product of their charges. Okay? The charge of the first ion, Q1, and the charge of the second ion, Q2, which is divided by, or which is inversely proportional to the internuclear distance, that is the distance between the nucleus of the first ion to the nucleus of the second ion. As a matter of fact, some textbooks will write this as RO2, that is the radius of the two interacting ions. Of course, the radius of an atom or an ion is described by the distance between the nucleus of that ion to the outermost shell. All right. So when you take it, okay, let's see if we can describe this. So take, for instance, you have sodium ion. Okay, sodium ion is 2 and 8. All right. So let's assume that what we have here is sodium ion. All right. This is sodium ion, and again we have chloride ion, which is 2, 8, and 8. Did you see that? So we're expecting that, of course, the chloride ion will be larger in size. Very critical. This is chloride ion. It should be larger in size because here we are dealing with 2 shells, here we are dealing with 3 shells. All right. So definitely this will be larger in size, and of course, the if there is bonding or if there is attraction, we're expecting for both of them, to show that, union. Okay, so 2 and 8. So definitely the radius of this particular ion is the distance between here and here. This is the first R, and the radius of this particular ion is the distance between this nucleus and, of course, the outermost shell. But the internuclear distance, okay, which is this D you are talking about, is the distance between this particular nucleus, all right, to this particular nucleus. This is the distance we are talking about, okay? So the radius of sodium ion is the distance between its nucleus and its outermost shell. That is R, first R, okay? And the distance, the radius of chloride ion is the distance between its nucleus and its outermost shell. This is the second R. That's why some textbooks will write, instead of this D, they write it R raised to power 2. That is the radius of the two ions. Okay, so definitely, but however, the internuclear distance is the distance between the nucleus of the sodium ion to the nucleus of the chloride ion, which is what we denoted as D. Like I said, sometimes they write it as R raised to power 2, which I have told you what I just explained here. All right, beautiful. So another thing that I'm going to mention as I proceed is that if the value of E is negative, of course, when you have the two charges being opposite, okay? So take, for instance, in sodium chloride, you discover that sodium, of course, is 1 plus, and chloride, which has the second charge, Q2, is 1 minus. So the product of the two charges is Q1, Q2, which means 1 plus multiply 1 minus, which will give us what? 1 minus charge. So what we just said, I want to say it again, is that the value of E is negative when Q1 and Q2 have opposite signs. Invariably, this is what we're going to have with all salt compounds, because salt compounds are made from cations and anions. So they will always have negative E values according to Coulumbs law. All right, so that's why we say that negative values of E is well understood, because this is what we have in most salt compounds, since they are made up of opposite charges, okay, which are cations and anions, and all the cations and anions ultimately attract each other to form an arrangement characterized by a lower potential energy. Again, when particles that are very reactive like sodium and chlorine combine, they make a compound that is lower in energy. All right, this is critical. When unstable or when reactive or unstable particles collide or combine, they make something that is stable, all right, that is lower in energy. That's why we say that reactions are energetically favorable. Okay, such reactions are energetically favorable because you are starting with particles of high energy and ending with a compound or substance of lower potential energy. This is beautiful. So there are two case scenarios here which is important we understand. The first one is the combination of cations and anions to make a salt. All right. Remember, during ionic bonding, what happens is that there is a transfer of electron from the metal to the non-metal in a redox reaction for us to have a salt compound. Okay. So the first process again is that electrons are transferred from the metal to the non-metal, and that ultimately ionizes those the metal and the non-metal. So ultimately, when there is a transfer, you have sodium ion, and when there is reception at the other end, so this oxidation, loss of electron, this is reduction, gain of electron. So when we have ionized those particles, ultimately, remember, there is now a strong attractive interaction between the two. All right. So when this becomes an ion, sodium becomes sodium ion, chloride becomes chloride ion by gain and acceptance of electron. Ultimately, there's now a strong attractive force that holds them together. All right. And you now form sodium chloride. Pay attention to the states of this matter. Here we have gaseous metallic ion. Here we have gaseous metallic ion. But ultimately, we have now formed a solid salt compound. Remember the kinetic theory of matter. Gases are moving faster. They possess more kinetic energy. That's why ions are moving. Okay, gaseous ions are always, moving faster. They possess strong kind of, kinetic energy. But once the union happens, they lower in energy, and of course, they form a substance that has a lower energy. So we started with gaseous particles. Okay, now we're ending with a solid particle. That means we started with particles of high energy, but we're ending with particles of low energy. Where did that energy went to? Energy can neither be created nor destroyed. So what ultimately happens is that in this reaction, some amount of energy was released. So this reaction is known as what? Exothermic reaction. That's why such reactions we have negative delta H, or negative heat, negative enthalpy. All right, this is very, very important to understand that. Okay, so pay attention to what I'm trying to say. Whenever particles are combining, especially ionic particles are combining to make an ionic compound, such process releases energy to the environment. That's why we have negative delta H value. Okay, and such reactions are said to be what? Exothermic. So you're starting with particles of high energy, and you ultimately ending with a particle lower in potential energy. So that means some amount of energy was released in the process. So if you are going from high energy to low energy, some amount of energy is released in the process. And what we have there is what? Exothermic reaction or exothermic process. Okay? So on the other hand, when you have, we are trying to pull apart ions, that is, you are trying to balkanize or break down an ionic compound into the component gaseous ion, you are doing the reverse of what happened. As a matter of fact, energy or heat is required for us to be able to break that ionic bond that holds sodium and chlorine together, for us to get their gaseous ions, to ionize this particular sodium chloride, to break them apart into their component ions, we require energy. So that particular process, that's energy is supplied into a system from the surrounding, is known as an endothermic process. So again, to break the ionic bond between sodium and chlorine, to make the gaseous sodium and chloride ions, we require energy. Energy is absorbed from the environment, and that kind of reaction, we have a positive delta H, and that kind of reaction is known as what? Endothermic reaction. Endothermic reaction that absorb or taking energy or heat from the environment. All right. So again, when particles, ionic particles, are combining to make stable ionic compound, which is lower in potential energy, it means some amount of energy was released. Pay attention to this, because once we start talking about energetics of ionic bonding, you're going to understand this, and it will help us to be on the same page as we make progress, okay? And again, conversely, on the other hand, for us to break that ionic bond or electrostatic attraction that was, formed ab initio when those ions combine, we need to supply energy into this particular system for us to yank apart those ionic bonds. But the key point here is that when energy was released, certain amount of energy denoted delta H was released. As a matter of fact, remember that energy is conserved. The same amount of energy that was required to form the bond, the ionic bond that combines sodium ion and chloride ion to make sodium chloride ion, sodium chloride salt, is exactly the same amount of energy that must be absorbed by sodium chloride or absorbed by this system to, of course, pull apart their ions again. The only difference is in terms of their signs, and those signs is telling us if it's negative, that energy was lost to the environment. If it's positive, that energy was absorbed into the system. However, the values must be the same. All right. This is very, very important that we understand it. Okay. So the values of the energy, the amount of energy that is released is exactly the amount of energy that must be absorbed to break the same ionic bond. The difference is the signs, which shows us that energy was released. Of course, this happens when ions combine. I say it, when ions combine to form a salt compound, energy was released. So we're looking at a negative delta H value. All right. But the same amount of energy must be absorbed, of course, for us to pull ions apart. All right. For us to pull ions apart, the same amount of energy that was released to make sodium chloride is the same amount of energy that must be supplied to sodium chloride to break them into their gaseous ions. Okay. The only difference is that in breaking them into their gaseous ions, energy is absorbed or taken into the system. Energy is required to activate the process. So we are moving from a low potential energy substance to high energetic particles. See, we are moving from solid again to gaseous particles. Gaseous particles are more energetic, they are more unstable, and they are more reactive than solid particles. All right? So this is very, very key that we understand it. So according to Coulumbs law, we can now describe the two factors that determines the strength of the attractive force between two ions. Or put it another way, on the basis of Coulumbs law, we can identify two factors that will determine the strength of ionic bonds within an ionic or salt compound. And those two factors, we are talking about the ionic charge. Okay? The ionic charge, and the second one is ionic size. These are the two factors that determine the strength of ionic bond or the force of attraction between two ions. As a matter of fact, the force of attraction between two ions increases as, number one, the ionic charge increases, or put in another way, as the magnitude of the charges increases. For this video, I'm going to lay emphasis on the first one, and in the next lecture video, I'm going to lay emphasis on the factor of the ionic size. So the first issue here is that the attractive force between two ions increases as the magnitude of the charges or ionic charge increases, and number two, ionic size decreases. Okay, the attractive force between ions increases, of course, as the ionic size decreases. So again, I'm going to lay emphasis on the first one in this video. In the next video, I'm going to show you how it works for ionic size. Okay, beautiful. So, for example, the ionic strength of magnesium oxide is greater than ionic strength of what? Sodium chloride. And this is key. All right, this is because the magnitude of the charge here is 2, and the magnitude of charge here is 2. The magnitude of charge here, of course, is 1. The magnitude of charge here is 1. We didn't write them because anything times 1 is itself. Okay, so the higher the ionic charge in the compound, the stronger the attractive force between those ions, the stronger the ionic bond. So recall that magnesium oxide is a neutral compound. This is because 2 plus and 2 will cancel out. But we must understand that the charge on the magnesium ion is 2 plus, and the charge on the oxide ion is 2 minus, which is the magnitude 2, and 2 is higher than magnitude 1 and 1. So you will discover that there is a stronger ionic bond in magnesium oxide than in sodium chloride. And this particular phenomenon is what, accounts for why calcium sulfate precipitates out of seawater or sea spray before sodium chloride. What we are ultimately trying to say, put in another way, is that sodium chloride happens to be more soluble than calcium sulfate. That is because the magnitude of the charge in the calcium ion and the sulfate ion, which is 2 and 2, is higher than the magnitude of charge on sodium chloride, which is 1 and 1. Do you understand it? So the higher the magnitude of the charge, the stronger the ionic bond, and the lesser the solubility. Okay? So sodium chloride has more weaker ionic bond than calcium sulfate. That is why calcium sulfate precipitates out, comes out as solid, all right, because of the higher strength, all right, of ionic bond that it has, when you are dealing with seawater, all right. Recall that in the seawater, you can get your sodium chloride, and of course, you can as well get the salt calcium sulfate, all right. But calcium sulfate precipitates out before sodium chloride because of the stronger attractive forces, which is first as a result of the higher ionic charges. All right. So exactly, if you look at here, you see that calcium is 2 plus, sulfate is 2 plus, which is exactly what we have in what? Magnesium and what? Oxide. Because this is 2 and this is 2, this is 2 and 2. So ultimately, sodium chloride has weaker attractive ion-to-ion interaction than in magnesium oxide and calcium sulfate. Magnesium oxide and calcium sulfate have stronger ionic bond, than sodium chloride. And this is because of the higher ionic charge. All right. So ultimately, as ionic charge increases, in an ionic compound, of course, the attractive force between the ions also increases, and hence the stronger the ionic bond. In the next video, I'm going to go into talking about the lattice energy, but I'm going to also use how the ionic size, effect of the ionic size on all of what we have just explained. I don't know if you got value. It promises to keep becoming even more exciting. What we are doing again is that we're painstakingly trying to see how we can touch the key foundational aspect of chemistry and help some of our students who are learners who are deficient in these foundational aspects clean up their chemistry. For some reason, some students were disenchanted at the introductory level of their chemistry. So this is what Chem Class with Dr. Lota seeks to achieve. For now, we're trying to clean out the basic aspects of chemistry of chemistry for all our learners world over who are passionate and followers of Chem Class with Dr. Lota. If you learned anything and this gave you value, please kindly like, comment, and share so that it can get to those learners that actually need some of the information we're dishing out. So until the next time, stay safe, stay away from trouble. Keep taking care of yourself, keep bettering yourself, and keep enjoying and bettering your chemistry with us here on Chem Class with Dr. Lota. I remain your humble friend, Dr. Lota Nokwase. Until the next time, stay safe and bye.